Go ahead.
Good morning, everyone. So this is the third seminar, as Dr. Lee said. The first seminar was covered some of the basics of quantum computing, what qubits are, superposition, entanglement, those sorts of things. And the second seminar, we covered some of the basic algorithms underlying AI. And today we're going to talk more about the actual instantiation of AI using quantum computing. All right, to do that, we're going to cover a couple of the big algorithms. We have the variational quantum eigensolver, as well as the approximation algorithm for optimization. So, please, here we go. So, as in earlier seminars, I talked about how we're in a noisy intermediate scale quantum era. That is that at this time, we have significant challenges with noise in quantum systems and a limited number of qubits. Right now, the best quantum computers have a little over 1,000 qubits. And so we are limited in that range on what we can process. We don't want to render images with a quantum computer. It doesn't make sense with the resources available. So what we're dealing with here is, at best, is we have composite systems. We'll have some mix of classical computing along with quantum computing to achieve our aims. So we're going to want to dedicate resources based on what each system is best at. You know, and we have this graphic in the upper right-hand corner that we can combine the data as well as the processing, whether we use quantum data and then send that to classical computers for processing, whether we use classical data and send that to quantum computers for processing, or purely quantum or purely classical. So a couple of the algorithms we're going to talk about as well is, like, for classification, we have quantum support vector machines. And I'm going to have an example that I'll show you on my Colab about that, as well as it's on the GitHub. For optimization, we have variational quantum eigensolvers that are much more efficient than classical computing for computing the eigenvalues and eigenvectors of a matrix, as well as the quantum approximation optimization algorithm. You know, we can much more quickly process optimization problems while avoiding the local minima problem. Instead of doing a steepest descent type scenario, instead we'll actually process the hypersurface, whatever we're working with, to try to find a global minimum. Additionally, with pattern recognition, there's quantum clustering, both in a static as well as a dynamic sense, and that we can cluster information points. And as well as it's interesting with the dynamic clustering is that due to the speed quantum has, we can go to it regularly for updates to understand how these clusters are changing and moving in our space.
Question about the classical to control. I think we are familiar with the classical computing, and then do you think transition is the big issue for now, right? So do you see that what is the easiest way to get some idea classical computing versus the quantum computing? Are there any tool maybe available for the translation tool?
Yes, and I use one in my example. So like Qiskit, which is the programming add-on for Python that I use with IBM. They have things where you pass it classical data and it does the conversion into your qubits for you. It's an important factor to understand, though, is that you have to encode your classical data in quantum data. It increases your circuit complexity. Okay, so you know it's that to manipulate those qubits, we're increasing the amount of computation and the time exposure that we have for noise. Oh, is this thing not working? Give me one moment. I haven't plugged in. Oh, the power cord doesn't help if you don't plug it into the computer. There we are. Thank you. So we'll first start with the variational quantum eigensolver. With this variational quantum eigensolver, and I'm sorry for my color choice, it looks great on the screen. But we're going to take quantum state preparation. This ties in what Dr. Lee's question was. We're gonna take our classical data, manipulate our qubits to represent that classical data. Then we're gonna pass it into a quantum module that is going to pass it through layers of rotation and entangling. And then we're going to, after having processed that data that way, we'll pass it back to classical computing. We'll give it to a classical adder, make a classical feedback decision, and then we'll feed that back in to the quantum computer. The reason this is really interesting is it's really suitable for optimizing our classical machine learning hyperparameters. So we can pass a set of hyperparameters to the quantum computer, have it process it via those layers of rotation and entanglement, have the classical machine learning run that, and then pass its output back to the quantum machine.
So which part is the manual design? Which one can be automated? For example, how do you know that how many different quantum modules required for my own problem?
Yes. So it's going to be largely based on. So we talked about how you not only need to represent the quantum states of your bits as qubits, but we're also going to have some error correction and what's called ancilla qubits for some of the control. So it's like with quantum, if you're going to entangle two states, you're going to need to use a controlled knot. And for that, you're going to need 2 qubits to represent that one classical bit. So that's going to dictate the number of modules you have there. Each module is going to be responsible for one specific hyperparameter with however many qubits it takes to represent that hyperparameter.
Do you have any general estimation how many qubit maybe is required for the computing of the one of the examples you are showing, right? So do you have any?
Yeah. So for example, I'm working on a example for our next seminar for a graph neural network optimization problem. Okay, with that, I have 2 sources and 8 sinks. Okay, and to represent that, I need 32 classical qubits because I have 2 edges between each one. Okay, so with those 32 classical qubits though, then I need about between 16 and 20 error correction and ancilla qubits. So that problem is, so it's going to be dependent on the number of variables in the architecture you're working with. And actually at the end, because this error correction, we keep getting questions about that, I've showed the Lindblad operators and some of the error correction algorithms. That way we can kind of discuss what that looks like and how you determine how many error correction qubits you need.
How do you bring the some underlying architecture, for example, using GNN or CNN or even support information, we have an underlying network there, right? And how do you bring the quantum layer or quantum functionality to the existing model? So it's largely an augmentation. The quantum layer that you're using is going to be largely an augmentation to your existing architecture. For this optimization problem, for example, I pass my adjacency matrix to that along with the the cost I have on the edges and the resources needed, the sinks and the ones available at the source. And it performs these rotations, and then it passes that optimization problem back to my classical computer. And with quantum, it's interesting that it's really good at things like traveling salesman problems that are NP complexity, where most existing algorithms have to either brute force a deterministic solution, or what we usually do is, random search kind of things, where we're not certain if we have the global minima or not. So we're able to pass that aspect to the quantum computer, then pass that back to our traditional for it to do additional processing that the classical is good at. So that is a good integration, like the AI solution with the quantum merging is the good option. Yes. How about the pure quantum? Right, and it's one of those things where with that, it's just the limitations we have. Quantum computers going leaps and bounds right now, but at the same time, 1,000 qubits, and like the example I like to use with that is that's what 4 ints is, that's 10 int 64 numbers. It's really limited.
So we really want to reserve our processing on the quantum computers for the essential tasks quantum is good at. And it's one of those things where there may even be tasks that quantum is better at than classical computing,
Yeah.
but we'd be willing to accept the cost due to our limited quantum resources.
I see, I see. I see, makes sense.
About the last part, it's suitable for optimizing neural network parameters.
Yes, sir.
So VQE actually, if you define a VQE problem, you define a Hamiltonian functional.
Yes, sir.
What's really good for some mechanical system or even atomic system, like
Yes.
a lot of particles, where you can define a physical energy function. But then for neural network hyperparameters, that's the number of layers, right? Those kind of things.
Yes, as well as other things
Some
like,
functional for you.
yeah, so, yeah, basically, and that's how we process it. We represent the network as a Fourier transform to the extent we're capable of, and then we pass it to the VQE. You know, and I'll be frank, I haven't implemented this myself yet.
Yeah, because I wonder about it too, because.
Yeah. Yeah, but, this afternoon or tomorrow,
Mhm.
I'll pull up some of the resources I pulled these statements from. And I'll
So
provide
they're
them
really
update
sure for that, right? For defining
Yeah.
like some
Yes.
function, you know, for
Yes.
hyperparameter. Yeah.
Yes. But I will try to today or tomorrow, I'll upload my resources on that.
Yeah, on the other hand, because like why using quantum computing for doing that, right? Because the machine learning traditionally, we know how to.
It's
Yeah,
it's the
validation.
search space on exploring hyperparameters is a big problem that's had tons of research over the last decade. It's the search space is so large that tuning hyperparameters is still more art than science. Because
Yeah.
yeah.
And cross validations, stuff like that.
Yeah, and I mean, there's aspects of that, but it's one of those things where
contact deployment and all other.
just due to the size of that search space,
Yeah.
how many of these different hyperparameters can
In the
tune?
meantime, the neural network model has to be in terms of quantum neural network.
No, this is gonna be for a traditional neural network. We're not gonna process a neural network on a quantum computer. What we're going to do is use. And I'm speaking from my limited knowledge, as I said, I haven't instantiated this yet.
Again,
Yeah, no, you-
also I'm curious about.
Yeah,
this.
yeah.
Just like.
I understand,
Yeah.
but we're gonna take the output of the network and feed that into the quantum computer
So.
for exploring the hyperparameters.
And thank you. And when talking about the search space, killing point of the quantum, from our understanding is that it can possibly reach to the global.
Yes.
Global minimum,
Yes.
but the thing is, when you are combining with a neural network, how can you guarantee that? Because you only like substitute only part of.
Yeah, and that's one of those things where, when we talk about the ability of quantum to find that global minimum, at this point, it's still we empirically know it's possible, but we're still limited by the number of qubits we have. So we're still accepting some degree of randomness and stochasticism, you know, but we're able to process, you know, the second order derivatives of matrices and stuff with quantum problems. So those aspects quantum can help our classical systems with much more. So that like.
Is it correct to like explain it as like if the surface, the solution surface, there's global minimums, there's global highs, right? So all this surface all in the dark, but the quantum computing gives us like even a brighter light to look around.
Yeah, I don't think it's a bad analogy. Yeah,
Okay.
you know, it's, I like that, yeah.
Okay, all right.
All right, quantum approximate optimization algorithm. I'm working on an example of this for our fourth seminar, where I'm using it for optimizing disaster relief processes for a like island nation like the Maldives. They have a couple large airports, they have hundreds of islands. You know, hey, if we have a large storm hit, take out one of these airports, one of these ports, cause damage to other areas, what is the optimum way to provide relief to, you know, an island that maybe doesn't possess one of these major airports? Okay, we've disrupted supply, we have higher need, what's the best way to handle that? So it's these optimization problems with this, so here, you're gonna use beta and gamma, all right, as our parameters to this that we're gonna find. And we have a two-step circuit where we have a phase operator. And with phase, remember, for anyone who wasn't here, I'll explain it, that typically we represent qubits on a block sphere. It's a three-dimensional sphere. And so a pure ket 1 state is at the North Pole, pure ket 0 state is at the South Pole. And we have both the phase and the positive and negative directions. And so with these phase rotations, we're rotating the qubit along an axis. So we're going to do. So what we're going to do with this is we're going to perform phase and amplitude rotations for this to increase the probability. It's at the heart of this, it does use Grover's algorithm, which I talked about previously for search, where we increase the amplitude of the ideal parameters. So instead of searching saying, I want to find this, we pass it our constraints and our formulation of the problem, and it increases the amplitude of the parameters that optimally solve that problem. All right, and it's a well suited for graph-based optimization, where, you know, if you had some basic graph theory courses, you know, where, hey, we're trying to model the most optimal way to route something from one place to another. The traveling postman problem, where it's like Amazon spends a lot of time trying to find the most fuel efficient way for its trucks to get from one destination to another. And the problem is that when you're talking about hundreds and thousands of nodes with even more than that edges between them, it's not a simple problem to solve in classical computing. And that's where this quantum aspect's better able to help us with those problems. Yeah, sure. All right, quantum clustering. So with quantum clustering, so much of like classification that we use, as well as the unsupervised classical machine learning, is trying to understand how to cluster items. Okay, what is the significance between an item being part of one group versus another group, and to try to use that for knowledge discovery. Quantum clustering, with its ability to process matrices, is able to help with that. So we encode the amplitude of the qubits that represent our data points, and we form a distance measurement, and then we form an entanglement layer. We're using this to process our space here to create that clustering. And the dynamic quantum clustering is really interesting because of quantum speed of processing these problems. It has a lot of interest for its applicability to dynamic environments, where an item at one time step may be part of one cluster, but another time step may be a part of another cluster. Because of quantum speed at processing these problems, it has a lot of promise. And also, since we're in that NISQ era, we do a lot of a limited basis approach, where think of something like PCA, where we reduce the dimensionality of the problem. We have 1,000 qubits to deal with. You know, we reduce the size of the problem to try to process it, but it has even more power than methods like PCA, because we're able to increase the level of complexity of our search.
Are there any specific distance measurement relevant to the quantum computing? For example, Euclidean versus non-Euclidean, right? But now it's a multidimensional problem.
Yeah. So it's one of those things where that distance measurement is being conducted on classical computing. I'm not certain of any specific quantum distance measurement. I'd like to look into that more, but as far as I know, that distance measurement is still being conducted on classical computing, and so it's going to take into effect one, what works best for the problem. You know, Euclidean distance is great for some aspects of clustering, whereas you might want a more angular distance if the magnitude isn't as important as the orientation. But we're still going to be largely limited by classical processing on that. So data encoding in quantum systems, all right, this is a significant expense with quantum, is that we have to use quantum computers to encode quantum states. So you have to realize that we can't just pass it the normal ones and zeros that our classical computers work on. We have to encode that into the spins of the electrons or a trapped ion. And so that takes time, and that also exposes us to the both classical and quantum noise aspects where we can lose information. So there's two major ways of encoding quantum data. We can either do it as amplitude, how, the probability of that state being one, or we can do it through angle with things like phase rotations to encode that data. So both have specific use cases. But it's one of those things, it's two major ways. We're gonna either increase the amplitude of the signal we're looking for, or we're gonna change the phase. And a lot of times we're gonna use something called quantum feature maps. I use that in my example today. And that's the process that automates that transition from a classical system to a quantum system. I use called a state vector feature map to transfer my classical information into quantum information before it runs on the quantum computer. Now, real quick, the challenges with quantum AI are all the same challenges we have with quantum system. The noise injected from classical sources like heat or interference, and as well as the quantum processes like spontaneous decay or spontaneous energy level drops. Sorry, physicists. But the decoherence, where we lose entanglement, we lose the integrity of our information, the qubit limitation, as well as quantum error correction. With quantum error correction, we have methods for ensuring that our quantum information isn't lost. In the simplest example I can give of this is instead of encoding information in 1 qubit, we encode it in 3 and then do a voting system. All right, where that increases the probability that we don't lose information. So there's a couple aspects that we have to provide for with quantum error correction. We can have bit flip, a 1 becomes a 0, as well as phase flip operations. And this here is Shor code that represents how we process this error correction to ensure that our information isn't lost. Additionally, there's Steam code, which is a 7-qubit code that comes from classical Hamming codes. Now, in the previous 2 seminars, I've had people ask me, how do you determine how many qubits you need to process this information? That's where we get into Lindblad operators. The Lindblad operators, what they provide for us is our probability of our bit flip or our phase flip. Then we can use that to inform which quantum error correction process is most desirable. So if we have a high probability of phase flip, we're going to use error correction systems that are more effective at that. And what we can do from that is determine the probability that the result we get at the end is our desired result. Okay, and so, through algebraic manipulation, you can run that the other way. You can start with the probability as well as the probability of phase flip or bit flip errors from the specific quantum computer you're using to dictate how many runs we need to do, how many additional qubits that we need to encode. And it's one of those things where I like to have the conceptual understanding, but also Qiskit, they allow you to see how many qubits you're going to use. You're allowed to input these things. You don't need to run this this formula to determine. Qiskit has those tools available to you. So this is everything we talked about. Before we get into questions, though, I would like to share the basic support vector classifier I instantiated this. So we have the installation of our tools and then our normal imports. And the thing I really want to impress on everyone is with the work that's been done on these quantum programming languages, you don't need to be a quantum physicist to instantiate this into your work. Most of this code you're going to see is stuff you're relatively familiar with a slightly different style. I'm going to set my random seed for my quantum program. Okay, I download my data, and this is all processing. You know, and I'm doing my normal statements here where I'm saying like, all right, what's the shape of my data? Okay, now, since we're working on quantum systems, I need to limit how much of this I'm working with. So I'm selecting 1,000 of these variables to run through my quantum system. And then I additionally limit it to 5 categories. So my features that I'm testing are duration, the type of protocol, source bytes, destination bytes, and the count. Okay, this is for a cybersecurity type. Is this malicious, not malicious, yes or no, classifier. Then I provided a scalar, you know, to my data, just like normal, keep between 0 and 1. All right, I split my data set. So far, this is all still classical computing. Okay, and then I need to do that quantum feature mapping that I talked about a little bit earlier. Okay, so the number of qubits I need to specify here is xtrain.shape. You know, what is the shape of my data? That's how many qubits I need to encode. Now, I want you to understand that this is the number of qubits I'm passing to the algorithm. This isn't necessarily the number of qubits I'm using, because we're going to have some error correction. We're going to have some information like that, but that's the inputs to my function. You know, and then I run that feature map where I map my classical data into quantum data. All right, in this example, I ran it on an error simulator. Due to the limited size of the problem, I was able to run it on a simulator. However, it's well empirically shown the quantum speedups that we have available. So I set my backend and as well as a sampler for my quantum system on how it selects the data to run. All right, and then I use my quantum kernel to evaluate the data. All right, now I take that information that I ran to my quantum kernel that I've had returned back, and I'm using a traditional support vector classifier to evaluate this. I run my normal predictions. Okay, and now I'm going to show the classification report. So overall, with a sample size of 1,000 and only selecting 5 of the available categories, we're able to achieve 99% accuracy. You know, we have our confusion matrix there, but this is just a little simple showcase of just how powerful these systems really are. This is a pretty small data set, you know, where I selected 1,000 out of 495,000 available. I limited the categories from 42, I believe, down to 5. I was able to use this support vector classifier. Now, you know, don't get me wrong, I chose the most advantageous 5 that I could, but all the same, it really showcases this power. You know, we can see this confusion matrix of a short limited run that we had, and this was an imbalanced sample. We had 158 attacks and only 40 normal. But, you know, it just showcases this capability where I'm able to use quantum for the problems that it is good at and pass that information back to classical computing to get an improved result.
So do you have any operation study how much improvement happening traditional?
Yeah, yeah, it's so there's going to depend on your problem and the metrics you want. So there's going to be time savings, where a lot of times with classical computing, I mean, if we run it as long, a lot of times we can get to the same problem. It's just the computational cost that quantum can save. But in situations where that search space is too large to explore, and quantum can provide you the definite answer, that's where the time savings happens. And it's I have lots of literature. I can try to post some on the GitHub. I'll post information about the eigensolver, as well as information about the quantum speedup. But by that simultaneous processing of all the states, we're able to, you know, one shot, although we have to have repetitions for our accuracy, but still one shot that solution as opposed to incrementally testing each combination. So,
This particular case, we don't have that regular classical SVM versus the quantum.
yeah,
SVM versus
so
quantum.
it's one of those things where I wanted to put together a toy example
Yeah.
where people could touch it, they could play with
Yeah,
it, they could
okay,
understand how everything
sure.
worked. But last week I demonstrated in my, for this one, I didn't run the operational study.
Okay.
Last week, whenever we were talking about how we were doing search with Grover's algorithm. I was able to show that significant quantum speed up that, and I don't remember exactly, but classical took like 3 minutes or something, quantum took 2 seconds. Just insane, exponential speed up in that search where we went from n items down to square root of n items, or iterations, that is. All right, open it up to questions.
So you said that optimization, quantum optimization can apply to different type, the process, different tasks during the process, right? But one of them, you said that data preparation, vector generation, that can be helping for some classical computing aspect. But do you see that in the either transformer architecture or GNN architecture, we do the iteratively learning happening, right? Whether we can have an optimizer to helping
Yeah,
the process,
no,
during the process.
it's definitely a use case, and we're in the nascent stages of quantum. But for problems where we can either split up the problem sufficiently, or we can fit the data or compress the data in a way to pass it to quantum, it has a significant ability, I believe, to be a part of that architecture. And it's, as I've been saying, in the near term, probably in the next decade, we're not replacing classical algorithms with quantum. We're augmenting classical algorithms with quantum, so. Nothing?
Okay, how about next seminar?
Yeah. So the next seminar,
Yeah, what is up?
I'm getting more deeply into the graph aspects that we can use quantum for. And whenever we're talking about quantum's really good at simultaneously searching large spaces, it's really good at working with matrices. It's a natural extension that if we're really good at working with matrices, we're going to extend that to the graph domain. So with that, I'm going to finish my optimization problem. I'm going to talk about, there's lots of really interesting architectures people are coming up with for the application of quantum computing to non-Euclidean problems, those graph-based problems.
Additional question is, you show that embedding technology for the amplitude versus orientation angle part in the estimation of the island optimization problem, right? But what kind of the embedding may be useful for the quantum plus AI? For example, GNN, we know that the graph embedding is important. Right?
Yes.
And then CNN, we don't need much embedding. We may need a feature.
Yes.
Maybe it's important. So what?
Yeah. And with that, so usually what we're going to do is we're going to take our function that we're trying to minimize, and we're going to pass our hyperparameters of that function to the quantum system. But our classical computer is still going to be handling much of that embedding space, that space where it's a lot of linear processing. But this item, we've been this item. Quantum does have applications for that simultaneity that it has to process items at once. However, it's one of those things where it's the cost benefit analysis, where how expensive is it really to conduct an embedding on classical computing versus quantum? So it's going to be dependent on the problem. I'd like to research that space more. I'll try to bring some more information with that to the next seminar.
On the talk of embeddings, and honestly, I don't know if this question would be solved for me just trying to create a quantum project. Also, part of my question also like, how one-on-one can I get with you, help me learn how to use the quantum? But
yeah, so over there, I got the QR codes for the GitHub and the Discord. For you to reach out to me, please. I'd be more than happy to spend some time.
I appreciate it.
Yeah, and it's additionally, these companies, whether you go through Microsoft, whether you go through IBM, they want people to learn how to do quantum computing. They need engineers, they need people who are interested, they need people who want to use their systems.
Mhm.
So with that, they have so many resources available. You know, I'm not just saying go do that, but I'd be more than happy if you want to sit down for a few minutes and go.
I
Yeah.
appreciate that. Well, then, main question would be for embedding. Again, I apologize if this
Yeah.
comes to not understanding how it would exactly work, but you said for like each feature, yeah, we should put that to like a quantum version of that feature as we pass it the system. For NLP, I can see us creating text embeddings with quantum, but then would one feature be just an array of that one text embedding, or we have to split that up with how the qubits work?
I haven't touched that.
Okay.
Like, you know, on a conceptual level, I can say, you know, you pass hyperparameters and stuff, but I haven't touched NLP aspects yet. But like I heard you, there's all the people who are interested in this space seem highly collaborative. There are notebooks all over the internet of people saying, I did this, I did this, I did this, I did this. You know, please take a search and see what people are doing. You know, and pick something, whether it's Qiskit, whether it's Microsoft's thing, and start playing with it, because if you know how to code in Python, okay, they're just adding a library to it. You know, it's you learn a new library and you implement these things. And there's people out there dying to show you. IBM has an entire course that would be a good college course on how all of this works. That will sit there and walk you through and show you how to program these things. Yeah.
Especially we are thinking about the kind of student organization or club. We continue about some of the training and education and implementation to the class project. We can be a research project. So we are actually starting with some discussion now, and then we also want to contact IBM or some of the company that they can give us some of the free academic resources, and then we have the students can use the quantum computing technology at the class level, research aspect. So that is the kind of ongoing activity. We have several faculty coming from civil engineering, computer science, and physics. We're also discussing about interdisciplinary courses and also for the physics students and then civil engineering students or computer science students. So I think it can be a very mixed interdisciplinary research, but we believe that this is which because AI, we reach to some point, we need some additional computing power, which is coming from. So this area of two part can make a big difference for the future. So thank you for your interest, and then we're gonna give you the one last one for this year in 2 weeks.
Yes.
Yeah. Okay, thank you so much. Bye. Oh, one more thing is please make sure that participating in Hackathon, registration for the Hackathon is deadline is tomorrow, and you can we have a hackathon competition on November 15th in Hillary Course Library 352. So please participate. Either individual is okay, team is okay. We have good prices available, and we have some industry coming, and we have some opportunity for internal job. Thank you.
You know, and just one last point in passing is that oftentimes I'm saying like, oh, you know, let's limit it. We have to fit in the qubits and stuff. But you know what I'm doing, and if you're interested in what I hope you do, is this technology is obviously advancing. Okay, so in a decade, there's going to need to be people who understand the technology that are now implementing it for more real world problems. Whenever we start getting to where, you know, IBM wants to by like 2035 have 1 million qubits. Now here's the thing, it's probably a stretch goal, it's probably a reach goal, but if they achieve a 10th of that, that's significant in the power that we now have available to us. So like, I'm trying to get ahead of the curve, which maybe I should have started 5 years ago, but you know, best time to plant a tree 10 years ago, but second best time today. Yeah.
I have one question. In the example you shown, you are using quantum computing only in the model training, right? But there are like some big companies which have so much data. So the big data processing also an issue. So can we use quantum computing in that sector?
So with this NISQ era, it's not high. It's just you can't process that amount of data, 1,000 qubits. You know, it's right now that's what we have to deal with. You know, it's not a lot of information, so we need to preserve that for the most critical operations. It's a good augmentation, but you don't want to do data processing on quantum computing at this time. All right, everyone, thank you so much for coming. I appreciate your continued interest.